du, right? Minus du, 1 plus u squared. Aha! Well, that's an inverse tangent integral, right? Because that the integral of 1 over 1 plus x squared is inverse tangent of x. And so there you go. Minus inverse tangent of u plus a constant. Now undo the substitution. Minus inverse tangent of the cosine of x plus a constant. And there you go. So these inverse trig derivatives, they do allow you to integrate some stuff that it looks kind of impossible to integrate unless you know about these derivatives, right? That's true. Well, I think that's a pretty decent shot across the bow of what you should know of trigonometry. We'll keep picking up things as we go on here. You know, eventually we're going to do trig substitution. In there, we'll discover whatever it is that we missed here. All right. I think this is a good start for the trigonometry part. So let's turn the page now to hyperbolic trigonometry. What's that about? So, you guys know the exponential, right? Now, did you know this? If I have a function, f of x, and it has in its domain both x and minus x, if its domain is symmetric about the origin, there's a famous and well-known identity. There's a trick that we can do. This is 1/2 f of x minus f of minus x, or rather plus f of minus x, plus 1/2 f of x minus f of minus x. What did I do? I added 0. You may have never seen this before, and that's fine. What's interesting about this identity I just wrote, which again, it supposes that both x and minus x are in the domain of f. What is the nature of these two terms? This right here, folks, is even. If you replace x with minus x, what happens with this? This becomes f of minus x, and this becomes f of x. So it's the same thing again. What happens when you replace x with minus x here? You get f of minus x, and then you get minus f of x. So this goes to minus what it starts with. In fact, this is odd. So what this little identity shows you is that any function which has a domain which is symmetric about the origin, in other words, it includes both x and minus x for every x which is in the domain, can be written as a sum of an even and an odd function. This is just a little bit of what you might call function theory. When you apply this general idea to the exponential, which of course is such a function, right? X and minus x are in the domain of the exponential. The domain of the exponential, all reals, right? This gives me this. Guess what? These even and odd functions, these even and odd, the even part of the exponential is called the hyperbolic cosine, cosh of x. The odd part is called the hyperbolic sine of x, or sinh of x. That's their definition. It should be striking to you how much these look like Euler's formulas, right? The complete relation between those is a mystery that you only completely understand in what we call complex analysis. Math 331 here, advertisement. Okay, I'm sure it's not on your DCP, but you know what? Who cares? See if you can get a waiver for psychology of relationships or something and replace it with complex analysis. Oh, I'm sorry, 150 is not part of the required DCP anymore. So whatever it is you'd like to get rid of. So I want to do a multiple disciplinary studies. My multidisciplinary disciplinary studies degree is going to have everything except missing one fluffy requirement. I'm replacing it with complex analysis because I want to understand how cosine and sine and cosh and sinh relate most deeply. Okay, I'm just talking. This kind of flexibility doesn't exist. We talked yesterday about this. All right, I go on. So it's quite beautiful, this idea. I mean, so cosh of 0 is what? 1. Sinh of 0. 0, right? And cosh, basically, the smallest it ever gets is 1. And it more or less looks like this. Sinh looks like that, give or take. All right? So to some, to a crude description, cosh kind of looks like x squared plus 1, and sinh kind of looks like a cubic. That's a lie, though. They're more interesting than that. These tails, what are the tail? What's the asymptotic behavior of these? What is cosh of infinity like? Well, let me not introduce that. I am more rigorous in here than that. Let me not use such language. As x goes to infinity, what happens to cosh? This term, that term goes away, right? So asymptotically, cosh x behaves like e to the x over 2. So cosh x goes like that. As you go to plus infinity, as you go to minus infinity, this piece dies, and it's like e to the minus x over 2 up, right? For sinh, as x goes to infinity, the e to the minus x dies, and you get positive exponential like that over 2. And as x goes to minus infinity, this piece dominates, that piece dies, and you get minus an exponential. So it's exponential growth on both sides. That's what these are. How about their derivatives? What's the derivative of cosh? What's the derivative of sinh? Sadness. Yes? And how do you know that?
I have it written down.
You have it written down? Right on that paper, Dr. Cook owns a Lamborghini Murcielago, or whatever the most recent one is. Is it Aventer? I forget. I haven't been paying close attention. Oh, but your pen is powerful. Write it down. Make your reality my reality. Wait a minute, you could be a president someday. You just write stuff, it happens. That's awesome. I mean, I'm assuming you have an argument, though, right? Or did you see it in Calculus 1? You saw it in Calculus 1? Oh, well, that's unexciting. What I was hoping you would tell me, being a purist and wanting to derive things, I differentiated this. The derivative of e to the x is e to the x. The derivative of e to the minus x by the chain rule is minus e to the minus x, which is that. So the derivative of cosh is sinh. And when I differentiate this, the derivative of e to the x is e to the x, but the derivative of minus e to the x is minus e to the minus x. But that minus cancels this minus from the chain rule, and it gets me back to here. So in a game of differentiation, we could be here forever, just going back and forth and back and forth and back and forth and back and forth, right? It's much more, there's no signs to remember, right? SIGN. So that's kind of neat, right? Let's see here. And so you might wonder then, what are the analogs of these things, right? Do they have what's also true for hyperbolics, right? Is there an inverse hyperbolic sinh? What's its derivative? Is there an inverse hyperbolic cosine? What's its derivative? What's the derivative of inverse hyperbolic tangent while we're at it? You know, how do we figure these things out? And can we use them? Start out with something here pretty easy. So if you look at e to the x times e to the minus x, that's what? Let me short manga style calculation here. This is e to the 0, also known as? Yes, 1. Thank you. And on the other hand, this is cosh x plus sinh x, right? By definition, and also by some common sense, this is cosh x minus sinh x, right? Because sinh is odd and cosh is even, by construction, in fact. What happens when you multiply a plus b times a minus b? A plus b, a minus b is the pattern. We get what? Difference of squares, aka cosh squared x minus sinh squared x is 1. Aha! So it looks like the Pythagorean identity has given way to something a little bit different, right? So that's kind of neat. How about tanh? How would we define tanh x? I'm running a help session in 3 minutes in here. She's not crazy. I mean, she might be crazy. I don't know. No, she's harmless. She's a good student. Cosh x. Sinh x over cosh x, right? So what's the derivative of tanh? Yeah.
Hyperbolic secant squared. I don't know what you would call that.
Hyperbolic secant squared, but let's work that out, yes? So d dx, unfortunately, Sprano said he didn't cover this in at least one section, that Calculus 1 that happened recently, so I have to put in some detail here. So if this is in reruns for you guys, I am so sorry, but don't worry. Sinh. So you're telling me the answer, but I'm trying to derive it, yeah? So what am I doing right now? This is the quotient rule, right? You know it, you love it. Surely you have not forgotten it. Let's see here. This is cosh squared minus sinh squared x over cosh squared x, right? So what's that? Now I think we're right where you told me to be. This is 1 over cosh squared, right? Which is in fact hyperbolic secant or sec squared of x. I mean, I don't know how to verbalize it. There you go. That's what it is, though. Yeah. Cosine squared plus sine squared being 1 is necessary for the derivative of tangent being secant squared, right? The minus that you get from the derivative of cosine and the minus in the quotient rule conspire to give you sine squared plus cosine squared, which is why we end up with a derivative being secant squared for ordinary trigonometry. But you gotta be careful. Some of the reciprocal rules have a minus where it wasn't before. You actually have to think through it a little bit. This is where I'll pick back up here tomorrow. If you want to work ahead, the next thing I'm planning to look at is what's the derivative of inverse hyperbolic tangent of x. All right. And hopefully I'll get through this hyperbolic stuff fairly fast so we can dive into integration. I'm eager to get to new integration techniques with you guys before the week is done. We'll at least do a couple of them. Maybe just one, but something. Enjoy your special convocation tomorrow. Hopefully I'll see you at 3:30. Something tells me I'll see you Thursday, but let's try for tomorrow. I just have this bad feeling. Bad feeling. Oh, thank you. Everybody get the roster? Everybody sign is here? Because I lost my sheet. I lost my sheet from yesterday somehow.
I like the lightsaber you used.
Oh yeah. Yeah, I got that for Christmas a few years back. Oh yes, please.